Hello everyone, welcome to machine learning. In this section, we're going to discuss classification. Specifically, we want to discuss binary classifiers. We'll start with the introduction of the MNIST dataset, which is one of the famous datasets that's used in classification algorithms, and followed by training a binary classifier using MNIST dataset. We also want to spend some time on discussing performance measures, how you are going to evaluate how good your classifiers are. And we also would discuss multi-class classification, error analysis, multi-label classification, and multi-output classification. First of all, you should be aware that classification problems, we're talking about supervised learning algorithm because the data would have labels. So let's look at MNIST dataset. It has 70,000 small images of digits handwritten by high school students and employees of the US Census Bureau. It has been studied a lot. That is often called the hello world of machine learning. Whenever people come up with a new classification algorithm, they are curious to see how it will perform on MNIST. So you see how important this dataset is. That's exactly the reason that we are going to use this dataset throughout of our learning process. So first thing you should understand, what is MNIST dataset? We're able to get MNIST from scikit-learn datasets by fetch OpenML class. And then the way you do it is so you fetch OpenML MNIST 784 version equal to 1 to get the MNIST data. Here are the key major keys for MNIST. It has data, target, feature names, description, details, categories, URL. We're going to discuss a couple of major ones among these keys shortly as well. So here is an example of the MNIST dataset. So basically, it's a bunch of digits that are handwritten by students and US Census Bureau employees. You can see that some of them are very well handwritten, so it's clearly a 5 or 0, but some of them not necessarily true. For example, this one is really a 5. So if you use a machine learning algorithm, there's a chance that will be detected as potentially as a 6, right? So just because of this this type of issues that exist in the data, so the algorithm will try to learn from what they say, what they see, and try to come back with some sort of conclusions. Learn from the data. That's the whole purpose of machine learning. So here from Wikipedia, you can see a bunch of classifiers, classification algorithms are applied on MNIST dataset. Specifically, you can see that the last column says error rate. You can see two of them, a couple of them, 3 of them, maybe the last 3, which are all related to convolutional neural networks and some sort of neural network system. And then it has specific details of that classifier. You probably don't know what these are yet at the moment, but that's totally fine. And then whether they did some sort of pre-processing of the data and what type of pre-processing was done for the data. So you can see a lot of researchers have done experiment on their classification algorithms on MNIST dataset. Let's also take a look at the first part here. Some of this name may be still new to you, but at least what we're trying to focus in this class is really focus on the top section of the algorithms. including k nearest neighbors, decision trees, linear classifiers, spot vector machines, random forest, and for advanced machine learning class, we are going to focus on the second part of the algorithms on this Wikipedia page in general. Okay, without further ado, let's continue with how we can leverage this data to run binary classifier. So the dataset itself has a key called description. It describing the dataset. Majority of the dataset would have this, especially from scikit-learn. So a data key containing an array with one row per instance and one column per feature. So imagine that your dataset would be just a data frame, and each column would be one feature that's related to the specific instance, and then each row would be just one observation or one instance. So you should clearly differentiate the difference between the rows and the columns. So let's look at this MNIST example. So let's say if we use X being the MNIST data and Y, lowercase y, being the MNIST target. So if you look at the dimension of MNIST data, it's 70,000 images, essentially. Each one of them look like 5 or 3 or whatever, and then we have 70,000 handwritten images, and then have 784 columns of data. We'll discuss what is that 784 about shortly, but for now you actually need to know it's 70,000 images, meaning it's 70,000 instances or 70,000 rows of the data. And as a result, the target would be 70,000 as well. 70,000 target, we know the label of the data. So the label is something that we already know, and it's something that's correct, basically. So how do you get that? It could be just some label-intensive work to label it so that we can use that as the truth, so that we're able to test our algorithm and methodologies. Okay, so once you understand that, let's look at how we can understand the data. So you can leverage matplot libraries, pyplot class to help you to understand the data. For example, you take one of the first one from your MNIST data, which is X, right? X0 is your first image. You take out that image and you try to reshape but to a 28 by 28 dimensions matrices. The reason that we do this is just because it's 784, which is 28 by 28. So essentially what this 28 by 28 data structure is storing is 28 by 28 pixels of the image. So if you think about this 5 being a square box, and then we split the data into 28 by 28 matrices, so each single smaller square would be represented by something from 0 to 255 to indicate how black that particular pixel is. And then as a result, you can imagine that certain of the cells of that matrix would be have a higher value, and some other ones would have a smaller value. So if you put them together, you would come back with a target, with at least estimated target, whether it's going to be 3 or 5 or 0 or 10, etc. We don't really have a 10 in this case, only from 0 to 9. Okay, and then you could show this number by doing this. So essentially here, it just indicates that the first image in the dataset is a 5. You could test on your algorithm to say, take a couple of random ones and see what the numbers are. And then you can also look at your target. The target y0 is lowercase y, right? Y0 is indeed 5. That's how you at least get a preliminary understanding of the data. Let's see how we can train a binary classifier. You identify one digit, for example, in this case, the number 5. So we call it as y underscore train 5. Y train underscore train 5 only takes all the observations when the y train equal to 5. So it's true for all the 5s, but false for other digits. And you do the same thing, you come back with a y-test data set. That's also y-test underscore 5 for the ones that are true for all the 5s and false for all other digits. You can leverage something called stochastic gradient descent classifier. I know this is something that is still new for you, but it's just one of the classifiers, and then you could leverage SGD classifier class from sklearn and try to train your data to see to train your data. Once you have that training model of SGD CLF, you could predict on some digits to see what the output would be. This some digits is the first digits that we saw in the previous slide, which is x0. That's why it is true to be 5. But here in this case, I want to emphasize what is this random state equal to 42. So the reason that we want to initialize the reason that we have this random state is trying to initialize starting point for SGD classifier. So imagine that if you don't specify random state equal to something, you start with a solution today. You start with a random initial solution today, and then come back with a solution at the end of the day. But after a couple of days, you're trying to run the same program. There's a chance that you come back with a different solution. It's only there's a chance. Some majority of the time it would be the same, but just because of the random state situation for the initialization, you may get a different results. That's why you want to set the random state to be a specific number that helps you to make sure the algorithm is initiated from the same state every time you run the algorithm, and you would get exactly the identical results. That's a major purpose. You should be aware. Now, once we have a classifier, next thing that we want to do is to do performance measures. We want to understand how good our classification is, and to move forward to evaluate them. So here, at one point, we mentioned previously that you want to split your data into training set and testing. It's as simple as this case. We're just taking the first 60,000 images as a training set and the last 10,000 images as the test data set. As you recall, we have 70,000 handwritten images. So we're basically taking 1 out of 7 of the data set as a test data set, which is slightly less than 20%. right? Slightly, probably less than 15%. So essentially, we're using 85% of the data, roughly 85% of the data as our training data set, and the rest of 15% as well our test data set. And then you could leverage something called cross-validation to evaluate your model. So you could, from sklearn, you could import this cross-val score class, and then to leverage your SGD classifier, use your extreme Y-train 5 being your objective, and then cross-validation of 3 folds. So it's 3-fold cross-validation and coming back with your accuracy of those 3-fold of cross-validation. Turns out to be around 96% for the first fold. Second fold was around 94%, and third fold was around 96%. Sounds like it's pretty accurate, right? So you're able to differentiate those 5s from the rest of the digits, and then you have around 94-95% of accuracy. However, one thing you should be aware, the data set itself only have from 0 to 9. Let's assuming that you have uniformly distributed data set in that data, then your 5 should be roughly around 1 out of 10, right? So roughly you only have 10% of data being 5. So we further did some tests here. Says, okay, what if we just say all of the data are not 5? Let's just make a prediction. This algorithm prediction is simple. Just say all of the digits are not 5. So if I make that simple algorithm to predict all of them not being 5, then how much accuracy I should have? Roughly should be around 90%, because I only got that 10% of 5s wrong. The rest of them, I just said not 5, which is correct. So roughly it should be around 10%. It's a simple algorithm to label every single one, predict every single instance to be not 5, have an accuracy of 90%, which really is this part to discuss, right? It's 90% compared to our 94%. Is it better? Is it significantly better? Purely looking at this accuracy is not the proper way to look at how good your model is. So listen very carefully, right? Here, you should be aware, we don't just want to use accuracy to be our evaluation criteria. With that being said, when you start working on your project, you should focus on other metrics, not only just accuracy. So what would be the potential metrics that you could leverage? Let's take a look. This is something called confusion matrix. I hope this is not new to you. If yes, just listen carefully. So what we do is we come back with something called confusion matrix. The confusion matrix is as simple as use your actual label and your predicted value to construct this confusion matrix. It's nothing but what I draw on the bottom right. So in terms of column, it is the actual value. It's not 5 or it is 5 versus your predictions. It's not 5, your prediction is not 5, or your prediction is really 5. So in this matrix, you have 4 elements. One of them is called true negative. Your predicted value is not 5, and it's actually not 5. That's called true negative. and then your prediction is 5, and your actual is 5 as well, then it's true positive. And then your false positive would be you predict it to be 5, but it actually not 5. Then it's false positive on the top right corner. And then on the bottom left corner, which is your prediction is now 5, but it actually indeed is a 5. That's called false negative. So you should pay attention to this matrix, know which element is for what, and what column indicates, what row indicate as well. In a confusion matrix, you could have some other ways to look at the accuracy. So for example, one of them is called precision. Precision is defined as TP divided by TP plus FP. So essentially, if you look at what I got here, you use TP divided by the summation of TP and FP. That output is called precision. The other one is called recall or sensitivity, or true positive rate. You use true positive counts divided by true positive counts plus false negative counts. This is a ratio of positive incidences that are correctly detected by the classifier. This is another view to look at the values. So which is identical to what I put there together. The top left is true negative, and bottom right is true positive, and bottom left is false negative, and top right is false positive. So something that you should be aware that the recall value is across what we just mentioned here for the second row, and the precision we're talking about this column. And then if you look at the precision is really that 3 out of all of those 4 instances. The precision is 3 out of 4, and the recall is 3 out of 5, just because you have 5 here, and then you only have 3. That's being the true positive. So it's 3 out of 5. We can further discuss that confusion matrix can be summarized by something called F1 score. F1 score is a harmonic mean of precision and recall, which is 2 over 1 over precision plus 1 over recall, turns out to be TP divided by TP plus Fn plus Fp divided by 2. Okay, this is another way to look at the confusion matrix. It's called F1 score. Let's think about this graph. It's precision and recall trade-off. Let's look at this threshold here. So on the right-hand side is the positive predictions, and on the left-hand side is all negative predictions. So let's look at the precision for this threshold. It's going to be 3 out of the 3 because all of the 5s are correctly predicted, so that there's no false positives there. That's why it's 100%. But on the left-hand side, let's look at the recall. Recall turns out to be not only these 3, but also these 3 are misclassified as negative. That's why your recall is only this 3 divided by this 3 plus those 3, turns out to be 50%. Let's look at another one. What if we use this threshold? What happens is you have 4 out of those 5 are correctly predicted being positive. So you have 80% of the precision, but on the other end, you only have 1, 2, 3, 4 out of all the 6 fives. It's only 67% of recall. So with different thresholds, you are trying to make a trade-off between the precision and recall. In different algorithms, you probably want to focus on different aspect of the metric. Could be you are looking for higher precision. It could also be you are looking for higher recall. So let's see next example. So this graph shows that it's really that trade-off that we just discussed. As the threshold change, your precision versus your recall turned out to be different. And for a specific example for this dotted line, precision is around 0.9 and recall is around 0.42. What if we put the precision and recall on the same chart, like what we saw here? Recall being the x-axis and precision being the y-axis. Great, you have found a 90% precision classifier. As you can see, it is fairly easy to create a classifier with virtually any precision you want. Just set a high enough threshold and you are done. But wait, not so fast. A high precision classifier is not very useful if its recall is too low. So you have to be aware of what you are after and will be able to evaluate how good your algorithm is. Even further, we want to look at something called ROC curve. So what is ROC curve? Let's look at this matrix again. So we already know this is precision. This part is a recall sensitivity or true positive rate. And then the first row you could leverage to define something called true negative rate. As you could imagine, it would be Tn divided by Tn plus Fp. And true negative rate is also called specificity. And then as a result, 1 minus that true negative rate would be false positive rate, which would be Fp divided by Fp plus Tn. And then it's also called 1 minus specificity. So here this slash is really stands for or, not division. Okay, it's just different names. And then in this case, we want to draw something called ROC curve. The x-axis is a false positive rate, FPR. So which is right here, use Fp divided by Fp plus Tn. That's our x-axis. How about the y-axis? Y-axis is true positive rate, which is this recall or sensitivity or true positive rate. This is called ROC curve. Let's look at exactly how we can digest the ROC curve. Before we do that, look at how you can get ROC curve from scikit-learn. From scikit-learn.metrics import ROC curve, you're able to come back with false positive rate, true positive rate, and thresholds. And then you are able to plot the ROC curve. And then correspondingly, there's something called ROC area under curve, which is ROC AUC score, which is 0.96. Mathematically, it's just the area under that ROC curve. It's called AUC. This last slide want to give you an idea on how you digest what you got. In this case, we have two different classifiers. One of them is this blue dotted line, which is that SGD we just discussed. And the other one is a random forest classifier, which is something that we're going to discuss later in the semester, a random forest. And then you can see that random forest looks like actually outperforming SGD, just as simple as the area on the curve is much higher for random forest algorithm comparing to SGD algorithm. And then how do you think through this, right? So essentially says for the same level of true positive rate, the false positive rate for the random forest is actually lower compared to SGD classifier. And then the bottom line is we're looking for algorithms that actually have higher area under curve, which is much closer to the top left corner. But that's something you're after. And then when you do your project, you have multiple algorithms when you want to compare them. This is definitely the way to go. All right, this is an introduction to binary classifier with some discussion of performance metrics. Thank you.